Calculating shear and moment in beams subjected to distributed loads. This video is a continuation of lecture ST08. In this lecture, we're going to see how shear and moment can be calculated when the beam is subjected to a uniform, a triangular, or a nonlinear distributed load. Let's start with a case of a uniformly distributed load. Consider a particular beam in this steel and glass house. The beam is a member of the skeleton of the structure. At its left end, the member is seated on a plate and attached to it using a few bolts. We consider this a pin connection, since the bolts don't sufficiently restrain the end of the beam from rotating. At the other end, the beam rests on a friction pad, which allows the member to elongate, say due to temperature change. For the analysis purposes, we consider this to be a roller support. So we're going to treat the beam as being simply supported. The beam supports a part of the roof. We assume the weight of the roof is distributed uniformly over the entire length of the beam. Suppose we have calculated the magnitude of the roof load to be 0.54 kilonewton per meter. The beam's length is 6 meters. We wish to calculate shear and moment at points C and D. We start by calculating the beam's support reactions. Here is the beam's free body diagram showing the reaction forces as well as the applied load. To write the equilibrium equations, once the free body diagram has been drawn, we can replace the distributed load with its equivalent concentrated load. The magnitude of the concentrated load equals the area defined by the distributed load. In this case, the area of the rectangle is 6 times 0.54, or 3.24. This magnitude has a unit of kilonewton. The load is to be placed at the geometric center of the area, which in this case would be at the midpoint of the beam. Then we can write the equilibrium equations this way. Solving them for the unknowns, we get, knowing the support reactions, now we are ready to calculate the shear and moment values. To determine the shear and moment at C, we cut the beam at its midpoint and draw the free body diagram for the left segment of the beam. We denote the unknown shear force at the cut point as VC and use MC for the unknown moment. Since a distributed load appears on the free body diagram, before writing the equilibrium equations, we can replace the rectangular load with its equivalent concentrated load, just as we did in the previous step. The magnitude of the concentrated load equals the area of the rectangle appearing in the free body diagram. The load is to be placed at the center of the area. Now we can write the equilibrium equations like this. Solving these equations, we get 0 for the shear force and positive 2.43 kilonewton meters for the bending moment. We can determine the shear and moment at D in a similar manner. Here is the free body diagram of the left segment of the beam after cutting the beam at point D. Here is the free body diagram after replacing the distributed load with its equivalent concentrated load. And here are the equilibrium equations. Solving them for the unknowns, we get negative 0.81 kilonewton for the magnitude of the shear force and positive 1.82 kilonewton meters for the bending moment at D. Now let us examine the case of the triangular load. Suppose we have a small rectangular concrete dam as a part of a residential irrigation system. For the analysis purposes, let's consider a 1 meter wide slice of the wall. Water pressure at the base of the wall is a function of the specific weight of water and the height of the wall. The height of the wall is 5 meters. The specific weight of water is 9.8 kilonewton per cubic meter. So the pressure at the base of the wall is 49 kilonewton per meter squared. And since the wall slice is 1 meter wide, base pressure per slice of the wall becomes 49 kilonewton per meter. Given that water pressure at the surface of the reservoir is 0, we end up with this triangular load distribution. We can view the wall as a cantilever beam being fixed at the base by a concrete footing. So let's draw the beam in a more familiar manner, like this. Suppose we wish to determine shear and moment at the midpoint as well as the base of the wall. To determine the internal forces at the midpoint, we cut the beam 2.5 meters away from its free end, then draw the free body diagram of the left segment of the beam. We can determine the intensity of the distributed load at the cut point using the height to base ratio property of similar triangles, like this. So the triangular load has a height of 24.5 kilonewton per meter at the cut point. Before writing the equilibrium equations, let's replace the distributed load with its equivalent concentrated load, the magnitude of which is the area of the triangle, and its location is the geometric center of the triangle. Now we can write the equilibrium equations like this. Solving them for the unknown forces, we get. Now let's determine the internal forces at the fixed end of the beam. In the case of a cantilever beam, shear and moment at the fixed support are the same as the support reactions, and they are determined the same way. We cut the beam very close to the support and draw the free body diagram of the left segment. Then we replace the distributed load with its equivalent concentrated load. The equilibrium equations for this free body diagram are: the solution gives us the shear and moment at the support. These forces also represent the support reactions. Finally, let's consider the case of a generalized distributed load. The design of the retaining wall on the side of the house requires us to consider the effect of a vehicular load placed on the backfill of the wall. For our analysis purposes, we're going to consider a 1 meter wide slice of the wall. We assume the weight of the vehicle acts on that slice. Further, we assume the weight acts as a concentrated load placed at the center of gravity of the car. The effect of the point load on the wall can be characterized using a nonlinear force distribution, like this. The equation for this curve is: here we have used 10 meters for the height of the wall, 20 kilonewtons for the weight of the vehicle, and 5 meters for the distance from the wall to the center of gravity of the car. Simplifying the equation, we get: viewed as a cantilever beam, the wall and the distributed load acting on it can be shown this way. Suppose we wish to determine the maximum shear force and bending moment in the beam which occur at the fixed support. We cut the beam very close to the support and draw its free body diagram. In order to write the equilibrium equations, we need to replace the distributed load with its equivalent concentrated load. Given the nonlinear nature of the load, we have no choice but to integrate the function in order to determine the total load. We also need to use integration in order to determine the geometric center of the load. Let's denote the distance from the left end of the beam to the center of the load as b. Then we can write: solving this equation for b, we get. So we can replace the distributed load with its equivalent concentrated load this way. Now we can write the equilibrium equations and solve them for the unknown shear and moment. They are: now that we know how to calculate shear and moment at specific points in a beam, we're ready to discuss shear and moment diagrams. We will do so starting with the next lecture.